Good morning. I am Mr. Ish. Thank you for joining me. We are looking here at a new topic, area of a surface of revolution. That revolution can be converted to the word rotation and you would be fine. In analogous terms, we're basically looking at surface area calculations of a solid. This is generally considered to be a difficult subject. When you're thinking about curves and rotations and the volumes that result, that is relatively easy of a topic. Surface area calculations are slightly more difficult. If you have a rotation of a specific curve over a specific interval about the x-axis, the formula is right there before you. Let S be the surface area calculation for this revolutionary solid that develops. Along the x-axis, lower limit, upper limit, 2 pi y. What does y here indicate? You're looking at a function in terms of f of x. Meaning right here would very much fall your equation in terms of y equals. You would have a function which is f of x or y equals, this equation would fall right over here. Then in a square root you're doing this, the arc length calculation, 1 plus dy over dx whole square dx. All of this can very easily come into this form. You're looking at a 2 pi, which you see right here, you have a y as you see over here, and then the ds. ds takes a part of all of this right over here. Basically arc length calculation involving a rotation or a revolution. When you're looking at a curve with regards to its surface area calculation, when it rotates or revolves around the y-axis, you have a bit of a difference. Your interval here is along the y-axis. Here the interval was along the x-axis, but you see a 2 pi and then an x. Here the x indicates your equation is in the x equals format and you're putting it right there. But here you're seeing a dx over dy whole square. Here you had a dy over dx whole square. With respect to dy over here, the abbreviated version is integral 2 pi x. Same x as this, the equation is in the x equals format and ds, and that ds is all of that combined right over there. So this is the format you have to keep in mind when you have around the x-axis, you look at that, around the y-axis, this right here is your framework. But again, remember the slight changes or the nuances that are involved. Surface area calculations of solids are generally a bit more difficult than volume determinations. The best approach here, since this is the first time we're talking about this, is to take two easy examples, one of this form, one of this form. Easy first because it will help us understand the technique, then we can up it up a notch or two in the future videos. The first example we look at here with regards to surface area of the solid calculation is this, y equals root x from an interval 0 to 2 along the x-axis, and we are rotating this around the x-axis. Very quickly, a representation is this, root x from 0 up to 2. When you rotate it or do its solid, you have this, but we're not looking at the volume here anymore of this entire solid that results. We're looking here only at the outer periphery. What is the surface area of this outer peripheral shell? That is what we're calculating. Remember the formula here. We have from a to b. A to b will be 0 to 2. We have a 2 pi. The equation must be here with a y, but the y here is a root x, so we can bring that root x. And then you know you have the arc length part coming over here. You have a 1 plus dy over dx whole square with respect to dx. Let's examine what this dy over dx is. You're doing y is equal to root x, and just implicitly differentiate it. You'll have a dy over dx come over here, then you'll have a 1 over 2 root x. This right here is your dy over dx, which will fall right here. So when I erase it, I'll bring it into position right over here. We have 1 plus 1 over 2 root x, and then in a square, all of which under a square root. But keep in mind, when you're looking around the x-axis, you're focusing on dy over dx whole square. Around the y-axis rotation, you're looking at a dx over dy with regards to your formula. Anyhow, let's bring in our intervals right here. We have a 0 up to 2. You can open this up, and let me open it up. You're bringing the 2 pi outside. You have a 0 to 2, you have a root x, and then here you have a 1 plus 1 over 4x dx. You can do the simplification here. You have a common denominator. You'll have a 4x plus 1 over 4x. It's easy part over here. You will have a 4x plus 1 over 4x. You can separate these among their individual radicals using the laws of radicals. This comes out here as a 2 root x, and you see that 2 root x. Let's not erase too much, but let's bring everything here. You have a root x, then you have a 4x plus 1 within its root, then you have a 2 root x dx. This 2 and this 2 cancel out, this root x and this root x cancels out. Now suddenly everything has become this. From 0 to 2 you have just this 4x plus 1 dx. Now you have to just do the integration of this. You can do a polynomial substitution. U is equal to 4x plus 1. du is equal to 4 dx, and dx is equal to du over 4. You have to do new intervals, u1 and u2, everything with regards to this. u1 is a 0 in place of the x, you get a 1. u2 is a 2 in place of that, you get a 9. Everything here now becomes pi. You have this over 4 divided by 4, bring it right outside. You have now from a 1 to 9, you have a root u du. It's not too hard, and I will finish this now for you, but I'll erase this and we'll do it. We have here a root u, but we can write that as a u to the 1 over 2. It'll be easier that way. When we do have a pi over 4, we do the integration. We have a 3 over 2 come out. We have a 9 and then a 1. This 3 over 2 flips to give you a 2 over 3. Think about it. It's a fractional flip over here, nothing more than that. You have a 2 pi over 12, which simplifies to a pi over 6. This algebra part is not the hard part. It was basically formulating the expression which is hard. You're going to put a 9 to the power of 3 over 2 and minus 1 to the power of 3 over 2. 9 to the power of 3 over 2 is really a 27. 27 minus 1 times pi over 6. You will have a 26 pi over 6, which if you simplify it, 26, you'll have a 13 pi over 3, and that right there would be your answer. The surface area of this resulting solid is a 13 pi over 3, and I want to bring a decimal answer for you. It is 13.6. Let's put right here. Surface area is equal to 13.61 units square. That right there is the surface area, and it should be a good answer. Our second example, and the last one for this video, is this. Y is equal to x squared. Along the y dimension, we have these 0 to 4, and we are rotating around the y-axis. If you're looking at a representation, you're seeing this. You have a 0, 0 here, you have a 2, 4 here. You're rotating around the y-axis, you're getting a solid which looks like that, but we're not looking at the volume here, we're now looking at the outer shell, the surface area of this outer shell. What is that? If you were to cut it and lay it open, what would be the area of that? The surface area, and that's how we have to proceed. Our equation here, as you know, is going to be, we'll bring the 2 pi out. We're going to look at it from a lower interval, c to d, but we'll put our actual numbers here. We have an x coming in here, but the equation has to be presented in the x equals format, which I will bring over there. We'll have a 1 plus dx over dy whole square with respect to dy. So if y is equal to x squared, then x is equal to root y, and you know that is not too hard. We'll bring everything here momentarily. If x is equal to root y, then dx over dy, which is your implicit differentiation of this, is equal to 1 over 2 root y, and there it is. You have everything you need now to plug in here, and I will plug it in for you. Everything in terms of your surface area calculation, integral becomes 0 to 4. You have a root y over here because x is equal to root y, and then 1 plus, you have a 1 over 2 root y whole square dy. Let's do some simplification and we'll bring everything together. We have a root y over here, then we have a 1 plus 1 over 4y. Common denominator, you'll have a root y, and then here you'll have a 4y plus 1 divided by a root of a 4y, which I'll write separately, which will be a root y times root 4y plus 1 divided by 2 root y. These root y's will cancel out, but then you'll also see this 2 and this 2 will cancel out. So let's cancel this out. All you have in the end remaining after all of this right here is just a root 4y plus 1. So allow me to bring that in for you. Root 4y plus 1. It takes a very similar track as a previous question. You have a pi 0, 4, and then 4y plus 1 or 1 plus 4y, it doesn't matter, order does not matter, and there it is. You can do a substitution technique. U is equal to 4y plus 1, and then du is equal to 4 dy. dy is equal to du over 4. u1 and u2 are your new items. You have to develop limits based on this. When you put the original 0 in place of this, you have a 4 times 0 plus 1, your u1 becomes a 1. But when you put 4 in here, you have a 4 times 4 plus 1, you get a 17. Then proceeding we have with this, the substitution, let's just create a little space over here. We're looking at everything now from 1 up to 17. We have a u to the 1 over 2 du over 4. But this, you see this over 4, I'm bringing it right out here with the pi. Because here u comes within the square root, we have that. We can then integrate it. We have a pi over 4, and we have a u to the 3 over 2 divided by 3 over 2. That divided by 3 over 2, I'm just flipping it around right over here. I'll have a 2 pi over 12, which will very easily simplify to a pi over 6, and you'll see that to be the case. that denominator 3 over 2 multiplies with pi over 4 when it flips to give you a pi over 6 when simplified. And you're looking at everything here from 17 to 1. You could write your answer in one of two ways. You can do pi over 6. You can have 17 to the power of 3 over 2 minus 1. That could represent your surface area. Or just bring a calculator and calculate this out and bring a good clean final answer. And that's how I would do it. 17 exponent 1.5 minus 1 times pi divided by 6. I get 36.176, which I round to 36.18. 36.18 represents the surface area with regards to the resulting solid, the surface area. We can do units squared, and that would be my surface area end result. So keep in mind everything I've shown you here. The area of a surface of a revolutionary or rotational solid is slightly more difficult in terms of calculation than a volume, but it's not entirely too tricky. Just remember two equation forms. You can always rewind back to the beginning of this video, and I've presented you the two templates or the equation forms that you need to utilize based on rotation or revolution on the x-axis or the y-axis, and everything else proceeds after that has been determined. Thank you for watching this video. Have a good day. Bye.